Okay, so the midterm as well as Hack 9 and Assignment 3 are they're trying to grade those as quickly as possible, but again, please be patient, because we have three things to grade this week. The majority of it hopefully will be out on time, but if it takes us an extra day or two to get the rest of it out, please bear with us and be patient. Also, in this week's retrospective, note that by the time everything posts at the end of the week, that'll be about 62% of the course points will have been assessed already. You've only got 2 homeworks left. You only have about 5 or 6 hacks and labs left. So we're almost at the point of no return, if not there already. So make sure that you're taking a good hard look at your grade, and if you're satisfied, great, keep up the great work. If you're not satisfied with the grade that you're earning currently, then now is the time to reassess and make a commitment to change. Otherwise, you might want to speak with an advisor. I'll have all the details and all the stats available in that weekly breakdown, but as of right now, it's actually pretty good. I think something like 35% of the course of the students in this course are earning an A. With about I think 10 or 15% B and so on, and all of that will be available in the weekly stats that we'll post at the end of the week. For today, though, we're going to turn our attention to the next module, which is a short module. In fact, I'll probably get through everything today with file I/O, because it's actually pretty simple. The entire time that you've been doing I/O, you've been doing file I/O. Because in a Unix system, everything is a file, including the standard output and the standard input. So much of what you've already learned about reading from the standard input or writing to the standard input, all you need to do is cut, paste that knowledge, and you know how to do file I/O. A file is essentially a unit of stored memory. Usually you think of it as on disk, but again, it can be anything. It can be directory. Directories are files. Buffers, like the standard input-output, they're files. A socket, you write to a socket, you read from a socket. That's how you do network connections. If you for one computer to talk to another computer, they open up a socket. That socket is basically a file. You write data to that file, and it automatically sends on to the other computer. You read data from that file, and you're automatically reading data sent by that other computer. A program is a file, both when it's stored on disk and when it's running in memory. You can also read and write from a file, and in this sense, we're going to look at the traditional meaning of a file, that it's a text file or a data file that you're reading input from, you're loading up that file, or you're writing to that file. The technical term there is persisting to that file, saving to the file, okay? We'll go ahead and call it saving to the file or writing to the file. Files can be plain text. The vast majority of files that you'll deal with here are going to be plain text or binary, or they could be plain text, but not intended for human consumption. This goes into something called EDI, which is electronic data interchange. For one computer to talk to another computer, to send data from one computer to another computer, you need a common data interchange format. That's what EDI stands for, electronic data interchange. XML, which is extensible markup language, or JSON, which is JavaScript object notation, or Base64 encoding. These are all plain text formats where you can encode a bunch of data, send it on to another computer, and if that other computer understands the format of that data, it can process that. The two computers don't even need to be running the same operating system, written in the same language, or anything. You can still have this universal data format going between them. The basic steps to actually read and write from a file, though, are you open the file, you process the file. That could be either reading or writing, and then you close the file. So it's a simple 3-step process. The most complicated step there is going to be step number 2. But again, you pretty much already know how to do this, and I'll show you why here in a second. All right. Let's see. So file I/O in C. How do we actually do it in C? Well, we need to first open the file. So let's go ahead and do that first step up there of opening a file. Right. So there is a special file star pointer type built into the standard library. Note that it is all uppercase FILE. and star, and so it is a pointer. Why is it a pointer? Think about a file stored in memory somewhere. At the beginning of the file, you need a way to say that I'm at the beginning of the file, or I'm in the middle of the file, or I'm at the end of the file somewhere. Well, how do you, what am I doing here? I'm pointing to a memory location. Stored on disk, stored in memory, doesn't really matter. It's all the same to see. It's a pointer. It's a pointer to somewhere in memory. Initially, it points to the beginning of the file, and as you process it, it goes through the file until you reach the end of the file. And to open a file, you use fopen, which is short for file open. It takes two arguments: the path and name of the file you want to open. This is a string, right? And a mode, right? What you want to open it up for. There are several modes supported, but we're only going to look at two of them. One mode is R, and I'll put that in double quotes here. Or another mode is W. What do you think those two modes stand for? Reading and writing, right? So if you're reading a file, that means that you're doing file input, right? And if you're writing to a file, that means that you're doing file output, okay? R and W is pretty simple. So let's go ahead and look at some examples here. Right? So let's go ahead and open a file called data.txt in the current working directory for reading. Right? So to do that, I will of course need a file pointer, file f, star f, give my file name. I could call it input, right? I could call it f, I could call it foo, I could call it whatever I want. I'm going to go ahead and simply call it f for now, right? And I'll go ahead and call fopen. Fopen returns that pointer upon success. Upon failure, what do you think it returns? What kind of a pointer indicates failure, that I was not able to open up that file because it didn't exist or you didn't have permission or something like that? Null, right? So fopen, I need to give it its two arguments. Both of them are going to be strings. If I want to open up a file called data.txt, well, my first argument is simply data.txt. And if I wanted to open it up for file input for reading, I should give it an R. And that's it. What if I wanted to open a file for writing in the current working directory? Right? I could go file. I'll go ahead and go G here, is equal to fopen. I'll go ahead and go with output.txt, right? Or let's go with output.dat, right? File extensions in Windows, they mean something. If you've got a file extension of .txt, Windows will interpret that as it has to be text. If you've got a .docx, it's going to interpret that as a Word file. They're completely meaningless in Unix systems, in Linux systems. You can call a file whatever you want. The operating system is not going to simply take your word for it. It's actually going to look at the file and try to process it. So I'm going to call it dat, right? That doesn't say that it has to be binary. It doesn't have to say that it has to be text. It's just some file name. And if I want to open it up for writing, then I would pass in a W. Note that even though it's only one character, I'm still passing it in as a string because that's what it expects. It's expecting a string because there are some modes where, like B+, which stands for binary appending. Don't worry about those. Again, we're going to restrict our attention to reading and writing only. But that's why it could have more letters in there, and that's why it expects a full string, double quotes. Okay. What if I want to use relative paths? Right? I want to open up a file, say 2 directories up, named data.txt. F is equal to fopen. I can just put that into my path/file name, data.txt. Oops. And open it for reading, say. Right? Dot, that goes up one directory. Dot again goes up one directory. So we're looking at the parent, and then the parent of the parent, which we call the grandparent. All right, and we're expecting the file to be in that directory. Okay. You can also use absolute paths. Absolute paths. Let me go ahead and just cut and paste this. If I want to open up something like, I don't know, Etsy passwd. Right? There we go. So passwd, what do you think's in there? Passwords, exactly. And it's starting slash. It's starting. That's a forward slash because it's facing that way. It's in the directory called, well, etc. But we in Unix speak we pronounce that as etc. Just like that website. Maybe that's where they got that. Etc. and then the password file. There's no extension on it. It's just a plain text file. Do you think we should be able to read that? Should we be able to read passwords? Do you think that that's a good idea? Probably not. We will be able to read this file because it does not actually contain passwords. Way back 20, 30 years ago it did. And then they realized, well, maybe not everybody should have access to that. So we're going to take the passwords out and put it into a different file called the etc password shadow file, or just the shadow file. And that's where the passwords are actually stored. But user information is still available in there. If you want to find out information about a user, their user ID, their default shell or something like that, you can open up that file. And we'll take a look at that later on. All right? In fact, let me go ahead and cut and paste that. Or this. There's the shadow file. That's what actually contains passwords. Again, if it fails, if open fails, it returns null. And it should certainly fail in this case. Why? We should not have access to this etc shadow file. Let's go ahead and try. Okay, I'm going to go ahead and open up this demo here. And let's go ahead and open up the shadow file and see if we can do it. So I'm going to go ahead and call file star f equals fopen etc password. This is the file that we can read and for reading. We probably can't write to that, though, as regular old users. And let's go ahead and check. If f is equal to null, then, I don't know, printf access denied. Right? Otherwise, else printf granted. Right? Access granted, we'll go ahead and then start reading passwords maybe if we can. All right, I'm going to go ahead and compile this and run it. And access granted. Right? Now I'm on my system here, so let me go ahead and SCP this up to CSE. Let's see if we can get access to some of those, some of your passwords maybe. Right? At CSE, there we go. And I'm going to go ahead and go on to CSE here. VCC, what did I call it? Demo.c. Right? Recompile it for this system, run it, access granted. And to show you that I can actually read this file, let's go ahead and just more it, etc password. Right? There. Now, there are lots of users here, and it's not exactly useless information here. Here's one of our learning assistants, though, Daniel. His user ID on this system is 2522. It's meaningless to us. He's an undergrad, so you're probably part of this group too, 115. His office, that's not his real office, that's just the CSE office. But there's his home directory, and there is his default shell. The default shell for almost everybody is going to be TC shell. Right? What's this X right here? That's where they used to store the password. And of course, now it's been redacted. Instead, what if I wanted to look at the etc shadow file? Right? There are several versions here. Permission denied, thankfully. If I tried to, so let's go ahead and try opening it programmatically. Let's change this to not the password, but the etc shadow file. I have to do this on CSE because if I did it on my own computer here, Mac actually stores them somewhere else, not the shadow file. And let's go ahead and go GCC on this and run it again, and access denied. That's because fopen will return a null pointer that you cannot have access to that. Similarly, if you opened up a file for writing to a directory that didn't belong to you, you would also be denied, and it would be given a null pointer as a return value. Right? So just understand that when it fails, it will return null, and you won't be able to work with it because if you try to write to null or read from null, nothing's going to happen. Right? And this could happen if you don't have read or write permissions, for example. However, there is another situation. If you do have read permissions or write permissions to a pre-existing file, then what happens, right? If you open a file for reading that, or for writing that already exists, it will be overwritten. So be careful, right? If you don't want to overwrite that, maybe you need to copy that file to another file and then open that up and then rewrite to it. If you open a file for reading that does not already exist, it will generally be created for you. Right? So if you start, it's not necessary to create the file and then open it and start writing to it. Just the very simple act of opening it, if it doesn't exist, it'll be created for you. All right. Once you are, sorry for writing, I should have said that. Writing. There we go. Once you are done with the file, you should, well, if you open it up once, again, step 1, step 2, step 3, open the file. We'll process the file. We'll cover that in detail here. But the last step here is going to be closing the file. You should close it, right? You should close the file. Well, if you use fopen or fopen to open the file, what do you think you use to close it? Fclose, for close, right? Right. And here's a full example. Suppose that I had that pointer from before, right? Let me go ahead and cut and paste it down here. And ... process the file. And once I'm done with it, all I simply need to do is pass that pointer to fclose, and it'll close the file for me. Failure to properly close a file may corrupt the file contents. Right? 99% of the time, it won't happen. 99% of the time, the operating system will save you from yourself and actually safely close the file. It's that 1% of the time that you have to worry about that I didn't save it and the operating system didn't save me from myself, and then the file gets corrupted. Right? So make sure that you're always closing that file. We've taken care of step 1 and 3. Now we need to take care of step 2. So we'll start with file output. Right? Plain text. We're not going to be doing much binary in here. If you are going to be working with binary files like image files or audio files or something like that, what you should do is use a library. You already did this in several of your hacks. We brought it. I didn't write that code to process the image. I brought in a library to do it for me, just because there's so much that can go wrong, and you have to know the proper file formatting for any binary format, and then you have to write code that adheres to that standard, like the GIF standard or the PNG standard or the JPEG standard. And so you have to then know all about encryption and not encryption, but compression and decompression for some of those things. You have to know all the usually they put in magic values or magic numbers to indicate that expect this file to be a GIF file of version 89 or version 99 or whatever it is. We're not going to deal with that detail. We're going to mostly content ourselves with working with plain text files here. Okay. So there are many ways to do file output, right? or writing to a file. We're going to focus on one. fprintf. What do you think fprintf stands for? File print formatted. If I took off that first F there, you would have your regular old printf. So everything that you know about printf, now all you have to do is cut and paste that knowledge, and now you know how to do file output. The only difference is that fprintf accepts an additional first argument. That argument is going to be the file handle, the file pointer, or sometimes we call them handles, to print to. Right? So it's really easy. All we need to do is open the file, fprintf as many times as we want. So I'm going to go ahead and do that here. Let me go ahead and rewrite this demo here. Obviously, I'm not going to be able to write to that shadow file. So let me go ahead and just open up a data.txt file in the current working directory. It's going to work, but you could leave that error checking in there if you really wanted to. Let's go ahead and print a line to there. fprintf, the first new argument that I give it is the file that you want to print to. After that, you provide the formatting. Hello, how are you? Right? And the line. And if there are no variables to print, then you would do this. If you wanted to print a variable value, 10 fprintf, then again, the first argument is going to be the file to print to. The value of x is %d and the line, and then you give x. fprintf, or let's do a string here. Char name is equal to Chris, right? And hello %s and the line, and we'll print out my name. Right? Now what should I do at the end if I'm done? For close f. Right? Let's go ahead and compile this and run it. Well, first of all, let me look at what's in the current working directory here. There's a bunch of unrelated stuff. Don't worry about that. In fact, let me go ahead and make a temp directory here, and let's move. Oops, it already exists. What's in it? Okay, so remove rf temp. Let's clear it out. Let's move the demo over into temp, and let's make a clean, there we go, compiling here. All right, and I'll go ahead and run it. Before I run it, I want to look at the files in there. It's just a.out and demo.c. I do not have a data.txt file in this current working directory, do I? But I will after I've run the file. There it is, data.txt. Well, what's in that file? Hello, how are you? The value of x is 10, and hello, Chris, and that's it. All right, all you need to do is use fprintf, and it's that simple. If you wanted to print a bunch of lines and go into a loop or something like that, you would put in fprintf inside of a loop. Whatever you want to print, it'll work. Let me go ahead and show you another. Let me go ahead and edit this again, and let's go ahead and get rid of this first one. Right? And let's run this program again. And what's in the data file now? Whatever was in there before got wiped out, and only the last two lines that I wrote are actually in the file now. You've got to be careful. Just blindly opening it up for writing means that it's going to start at the beginning of the file and start writing there, overwriting everything else that was already in the file. So if you need to save that file, you need to back it up or something like that, because there's not any prompt here that says, are you absolutely sure you want to overwrite this file? Are you absolutely sure you want to do this? The only way to enforce that is to get into Unix stuff like chmodding everything out, like 000 of data.txt. Let me run this again. It'll probably be a segmentation fault here. Yep. Why? What did I do to this file? I took away my own writing permissions to it. LSLA. Right? So this is read, write, execute, read, write, execute. I took everything away from data.txt. I can't read it, I can't write it, I can't execute it. Neither can nobody else because of what I just did. That was change mod or change the permissions basically. And if I tried to read it and write it again, then I denied myself basically. Let me go ahead and chmod it back. 644 is probably what it should have been. Data.txt, LSLA again, and you'll see that I restored my permissions to it. So that if I run that one more time here, of course, it's going to run now because I have read and write permissions again. Right? Again, it's going to fail. You need to do some error checking so that it doesn't just end in a segmentation fault like that. But otherwise, output fprintf, and that's it. Right? There are a couple of other dozen different ways of doing it, but keep it simple. Right? One way to do it is the best way. Right? What about file input? Again, there are many dangerous ways to do file input. Right? I'm going to limit it to two safe ways. Right? Basically, it becomes dangerous because a file, you don't know what's in there. If you want to read a line from a file, you're not going to know up front how long is that line. It could be 1,000 characters, it could be 100 characters, it could be 0 characters. If you just say read a line, there's no way to predict how many bytes you're actually going to read from that file. And if you're going to be storing that somewhere, there's no way to predict how big that needs to be. So what you need to do is you need to use safer ways. The ways that are safe are the ways that automatically limit the amount of data that you read from a file at one given time. The two ways that I'm going to show you are you read character by character by character, one character at a time. There's no way to get that wrong. If you've got a char variable, you read one character into that char variable, that's all it can hold. There's no risk of overflowing that buffer because it's not even a buffer. The other way that I'm going to show you is to read at most a certain number of characters. And then if you've got a string that can store that, then you're good to go because it won't go beyond that string. If you only have a string that you want, you're reading in file input from a file, and your string that you're reading it into is only 100 characters length, and the line is like 1,000 characters length, obviously you're not going to be able to store that in your string. So what you need to do is you need to use a different method that says limit it to as much space as I've got allocated for you in that. We call them buffers. Okay. The first way is fgetC. Right. Reads a single character from the file and returns its value. Right. It also advances the file pointer to the next character. Because as you're reading a file, if you want to read it character by character by character, well, you need a way to advance through the file. So if you call fgetC, which stands for fgetCharacter, it's going to get the first character and then move the pointer over to the next character. Then the next time you call it, it's going to give you that second character, then the third character, then the fourth character. It automatically advances that pointer through your file for you, so you don't have to worry about anything to do with the low-level file handling or anything like that. Let's go ahead and write or rewrite this demo here. Emacs demo.c. So instead of reading this file, or instead of writing to this file, let's go ahead and read it. Right? In fact, let me go ahead and change the file entirely. Let me go ahead and change it to Lorem. Is that how you spell it? Let's see. Lorem. There we go. My Latin is wrong. Right? So if you ever need a placeholder, Lorem Ipsum is the place to go. Lorem. So if you're doing layouts or something like that, and you don't have content yet, like if you're doing newspaper layouts and you just want words in order to fill it out and make sure that this picture goes here and then the words are right here, then you use placeholder text. And the classic placeholder text is Lorem Ipsum. It's just some, some Latin saying or whatever. You also have modern versions, like here's an actual translation if you wanted it. I'm just going to take the classic Lorem Ipsum here and cut and paste it and bring it over into a file. Right. Save this file. I called it Emacs lorem.txt, say. All right, there we go. Now all that is probably one line, so let me go ahead and actually insert some lines here. Right. You can never go wrong with Lorem Ipsum because it's just nonsense. I don't know if it's actual nonsense, but it's certainly not meaningful for most people, right? Unless you read Latin, and then you can translate for us, right? So let's go ahead and open up that Lorem text for reading. And I'm going to read, I don't know, let's say 100 characters. For int I equals 0, I is less than 100, I plus plus. Right? I'm going to read a character, so char C, and I call fgetC, passing in the file pointer. That's going to give me the next character. Let's go ahead and print it out. Printf, what's my placeholder for a character? C, %C. I'll go ahead and print them out one to a line here. Right? And I'm only reading the first 100 characters, the first character through the 100th character, or when I is equal to 99. There's certainly more than 100 characters there, so I'm pretty safe here. Okay, so std, I'm on CSE, sorry, C equals GNU 99 is what I want. There we go. Run that. Okay. Ooh, what was wrong? Oh, I know what was wrong. I should be listening to my compiler. Let me go ahead and compile this again and ask the compiler what's wrong. I forgot WAL because I'm on CSE. I have that by default on my own computer here. What was wrong? Printf warning, %c expects a matching int, but what did I give it? Nothing, right? And then warning unused variable c. Well, that'll be taken care of with this also. So comma c. Now I'll actually be printing something instead of just that random question mark. All right, and let's run this. There we go. There's that lorem ipsum text, 1 character per line. Lorem ipsum dolor amet. I don't know what that is. Right, then there's the comment, comma, then there's the space, and eventually we're going to have double lines here because it actually printed the end line character right there at the end of the first line. Okay? Well, that's the first 100. I could do the next 100 and go 200, 300. But if I did say 10,000, what do you think would happen? Let's find out. I'm interested. Prints nonsense. Why? The file's not that big. How many characters are in that file? Let's go ahead and look in Lorem. This tells me that there are 454 bytes in there, 454 characters. So how do I tell when I'm at the end of a file? I'm going to change this into a while loop. First of all, I'm going to do char here. Char is equal to, I don't know, it doesn't matter. I'll go ahead and set it equal to the null terminating character here. While c is not equal to, I believe that, I have to double check this really quick. Yep, okay. EOF, I think it is. There we go. And let's see if this works. Otherwise, it might be EOF. No, I think it's EOF. Let's go ahead and try this. If it compiles, that is. Yep, it worked. So, what is EOF? End of file. That's what that stands for. So if you are reading a file and you get to the last character, it'll give you the last character. If you then it'll advance it to a very special flag variable called EOF. And any subsequent call to fgetc on the same file that's open will result in EOF. And you can check this. Right? I think that this is defined either in the standard input-output library or the standard library. And it'll only go to the end of the file. I compiled it, but I did not demonstrate it. So let's go ahead and demonstrate that now. There we go. Run it. And it goes all the way to the end. I go one more, mistakenly, I think, at the end. But otherwise, there's the last thing. That's that ending double quote there. Right? So the takeaway from this is that you can continue to read from the file character by character by character, and at the end of a file, it fgetc, that is, fgetc returns a special EOF, which is again end of file character. It's not really a character. It's not a character in the ASCII text system. It's actually, I think, -1, which is beyond the ASCII text table because it starts at 0 and goes up to 255. So EOF is typically given a -1 value. We could probably test it what its value is and output it if you really wanted to. I'll let you do that on your own though. So that's character by character. Character by character, you can do it, but it's going to be very, very inefficient. In a modern computer, the slowest thing you can do is input and output. If you're just doing stuff in memory, number crunching, you're keeping everything in memory and on the processor, everything is blazingly fast. It's when you have to go to and actually write to disk, or virtual memory has to write to disk or something like that, or read from disk, then it gets super, super slow. Even if you have an advanced SSD drive that's super, super quick, it's still going to be the #1 bottleneck in any of your programs. It's going to be slower than anything else that you can do usually. So, to speed it up, you can go instead, you can read an entire line from a file, right? Using fgetS. So if fgetc stood for file get character, what does this stand for? File get string. An entire line if you really wanted to. Okay? Let's see. Let me go ahead and cut and paste this. Fgetc There we go. I just want to bring this over because it has the actual signature here. Sometimes I just like to call it forgets to shorten it up. fgetS gets up to a single line, but it's limited in the number of bytes that you specify. So again, it reads an entire string from a file, and it has this. So the first argument is the string that you're going to read the contents into. The size is your limit. If you say that you only want to read at most 100 bytes, it'll actually only read 99 bytes. Why does it read one less? What do you think? Because of the null terminating character, which it automatically takes care of for you. Great. No guesswork there. And then the last argument here is the file stream that you're reading from. Right? So again, each one of these in turn, S is the string that the contents are loaded into. And it needs to be big enough. It needs to be big enough to hold however much you are reading. Right? It's your responsibility to do that. The second one is, what is it, size? Size is the limit. It fgetS, if it gets, reads at most size -1 bytes from the file. -1 to accommodate the null terminating character, which it automatically inserts for you, right? And then puts it into, of course, S. But it stops when it sees the first end line character. So it reads an entire line. If your line is only 10 characters, and you said, well, okay, my buffer size is 1,000, it's still only going to read those 10 characters. It only reads up to and including that end line character. Right? So note, here, I'll put a note here. Note, fgetS retains the end line character in the resulting string. Right? And then finally, of course, the what did I call it? Stream. Stream is the file you are reading from. Right? So you do need a buffer to read in line by line by line. The size of your buffer, you could go through and find the longest line if you really wanted to, and then dynamically allocate a string that's big enough, and then close the file and open it again and then read everything again. Or you can just guesstimate something large enough that will take care of most situations. Or write even more advanced code where you read an entire line, and then if you didn't read that end line character, well, then you know that, well, there's more stuff on that same line, so I'll go ahead and process this buffer, then go on to the next, the remaining part of it. Okay. So let's go ahead and do the same thing again here, but using fgetS. Right? So let me go ahead and create a buffer, which is going to be just a character array, char. I'll call it buff, and let's go ahead and make it. Let's make it 1,000 characters long. Right? Now that's a static allocation, but it's small enough that it's okay. 1,000 bytes on your call stack, that's not that big of a. That's not that much. If you were doing an embedded system, certainly you would want to really take a close look at this and see if that's too big. But we're not on an embedded system here. 1,000 bytes, that's nothing. Right? But if there's a line that is more than 999 characters long, including that end line character, then I'm out of luck here, because I'm not going to be able to read that entire line in one shot. Right? I'll leave the while loop here, but we'll come back and understand, because you can't guess how many lines are in a file up front. So we'll still need some sort of a stopping condition. And I will call fgetS. Right? And then I'll also print it out. I'll leave that for a second here. Again, the first argument is the buffer or the string that you want the results stored into. The second argument is the maximum number of bytes that you want read. So it's -1 because it wants you to have the same size here. And so it doesn't want you having 1,000 here and then 999. It doesn't want you having to do that the arithmetic in your head. So we're going to match the buffer size here. And we're going to be reading from the file. Right? Now this is an entire string, so instead of a single character, we'll be printing out the string. And it retains the endline character, so I don't need to print the endline character. Actually, let me leave that in there for a second. And then I'll be printing out the buffer here. Okay? Now, how do I know when I'm done or not? It's a little bit different here. Forgets also returns a value. It returns a character pointer, char s, and I haven't used s here, so I'll go ahead and use that. And I'll set it equal to, or I'll just leave it like this for a second. Forgets actually returns a character pointer. When it gets to the end of the file, what do you think it returns? What kind of a pointer would indicate you're done or failure? I can't read another line because there is no other line. It's going to be null, right? We're going to capture this in here so we can check for it. While s is not equal to null, then go ahead and read the next line. Because the current line is not null, not null, not null. Read it, print it, read it, print it, read it, print it. Only when you get to the last line, okay, then you read it and you print it. Now it goes past the last line. We're at the end of we're beyond the end of the file. And you keep asking it, give me the next line, give me the next line, give me the next line. All it can return is null. And also it doesn't touch the buffer anymore. So that last line that it read will be retained in there, but that's not that big of a deal. We're not even going to process that. Yeah? That's a good question. You could get away with it if you did something like this. That's not a great practice, though. So if I need to initialize something for the first time before I start a loop, I should be doing that. S is equal to forgets. Right? That will give me the first line. Then I'll go into the loop because it's not going to be null unless it was an empty file. If it's an empty file, then you'll immediately get null and it won't read anything because there's nothing in the file. But what will happen now in my first while loop here? Will it actually print out the first line here? No, why? It gets the first line and then goes into the loop, gets the second line, and then prints the second line. Let's go ahead and try it and see what happens. Right? There's the second line. If I looked at Lorem, right, that's the second line. Right? It completely skipped the first line. So if I'm going to do this, I need to restructure my while loop. What should I do so I can print every single line? Switch it, right? Put the print first, then read the next line so that you're setting yourself up for the next the next loop through the file. And if I do this, right, and run it, there we go. Now I get every line. There's that first line again. But it's double spaced. Why is it double spaced? Because the end line character that it read from the file is retained in the buffer, and then I'm printing an extra one here. So if I didn't want that, I could of course get rid of this. Or another common operation is it is common to trim, or here's another technical term, chomp, the end line character from the buffer. Right? How do I chomp it out? Right? That's what it's called. It's called chomping. I think it comes from Perl. Because there's a function in Perl called chomp, and what does it do? It takes out any trailing and maybe, I think, leading white space. But we're going to chomp out that endline character. Right? How do we do that? Before we print it. So I've got buff, right? I'll want to set the last character, which is the endline character, to, if I want to get rid of it, just set it to the null terminating character. Now, how do I get the last character? Where is the last character? If I read in HELLO, where is it going to be? 0, 1, 2, 3, 4. But then there's that endline character, so it's actually going to be at 5. Right? But how do I know that? And how do I tell the size of the string? strlen, string length, right? Of buff. Now let's go through that again. HELLO, and then the endline character, then the null terminating character. How big was that? 1, 2, 3, 4, 5, 6. Where do I want my index? 0, 1, 2, 3, 4, 5. So what do I need to do? Subtract 1. Right. Let's try that. Oops. Let's try that again. Oops. If I'm going to use string length, what do I need? The string library. There we go. And run it. And there. Now it's single spaced. And if I didn't want any spacing whatsoever, I wanted to print out this ridiculously long line, then I could do that as well without printing any end line characters. And that again, and it's going on different ones, but you know, if I change this out, then it'll end up being on. Wow, I can't believe I can go across 2 screens here. I think I could get it across 3 screens actually, but there. That's all actually just one line. It's just going on to the next line because of it's too small. Okay. All right. So I'm going to go ahead and cut and paste this demo that I just did, or a version of it, so that you'll have it in the notes. And there we go. So there's basically the same thing, but with a different file. Okay. So yeah, question? No? Okay. Then again, the takeaways on this: forgets, retains, end line characters. Right? You can always chomp them out if needed. You can tell you are done reading from a file because forgets returns a char star pointer. Oops, sorry, pointer, which will be null at the end of the file. There we go. Ah. Okay, it's just going to the other the next line there. Okay. In contrast, fgetc, since it returns a character, it actually returns an integer, but characters are integers in the world of C because of the ASCII text table. In contrast, fgetc returns a special EOF flag value. Right? So null for fgetS, EOF for fgetc. It depends on how you want to read from your file, character by character or line by line. Right? Now, I said that we're not going to work closely with binary data, and we aren't, but I do want to give you a demonstration because you'll be doing this in lab next week. So let's go ahead and talk about, tomorrow, binary data in C. Right? So in C, C provides 2 functions, fread and for reading binary data, reading binary data, and fwrite for writing binary data. Right? I'm going to cut and paste this because they have basically the same signatures. There's lots of stuff in there. First of all, it takes a pointer, then a size, then nm, that's the number of items that you actually want to read or write, and then the file stream that you want to print or print from or print to. I'm going to show you how to use this. All right. First of all, let me go ahead and go back into this demo here. And let's go ahead and get rid of, let's open up 2 different files. So file F, instead of, for writing that is, we won't worry about reading. Let's go ahead and open up data.txt, and I'll go ahead and go with G is equal to fopen data.bin. I'm just giving it that name. It doesn't, you can't read anything into that name. I'm just calling it that because we're going to actually be writing binary data to it. And this is also for writing. All right? So I've got 2 files open here. What I'm going to do is I'm going to print out a bunch of numbers. So for int I equals 0, I is less than, I don't know, 100, I plus plus. We'll print out 100 numbers, 0 through 99 in each of these files. So with the plain text file, to do that, all I would need to use is, how do I output plain text again? How do I print to a file? printf, right? And I'll just go ahead and print %d. Oops. What's the first argument? The file that you're writing to. Then the format %d. And I'll go ahead and end the line here just so that we can actually see it. And then I. There we go. And then at the end, I'll want to close it for close, F, and I'll for close, G. Right? Before we get to the binary part, let's go ahead and make sure that this works. Right? I don't trust myself here. There we go. And run this, a.out. Okay, more data.txt. There they are, 0 through 99. Okay. Now let's go back in and edit this. Not only do we want to print to the text file, but we also want to print to the binary data file. Now, again, here's the signature of this function. I need a pointer to the thing that I want to print. So fWrite. I want to print I. How do I get its pointer? I is just a regular old variable, right? How do I change a regular old variable into a pointer? Ampersand. I heard it. Ampersand. That is the referencing operator. Ampersand is you go from a regular variable to a pointer, ampersand. You go from a pointer to a regular variable, that's dereferencing, that's going to be the star operator. So I want I. The size of this, how big is an integer? How many bytes do you want to write? Should I go 4? Nope. What's best? If you need to create an array to hold 10 integers, 10 times size of int. Right? The third one is how many items do you want to write? Well, I just want to write 1. Right? And then finally, the stream that you want to write to, I'll write to G. Right? There. Let me bring this back up. GCC it, and let's run it again. Everything is great. We've still got our data.txt file and our data.bin file. If I opened up the data.txt file with Emacs or something, data.txt, it's plain text. It's human readable. A human can understand this. Oh, it's 0 through 99, 1 to a line, right? It's legible. It's understandable. But that's because it's plain text file. It's just ASCII text. What about that .bin file? First of all, let's find out what kind of file it is. It's data, right? Do you think we're going to be able to make heads or tails of this if I open it up in a text editor? Let's find out. There, it's just garbage to us. It's trying to interpret each one of those integer bytes as, in fact, there are 4 of them, so it tries to interpret each byte, which is one number, as 4 ASCII text characters, and clearly it's failing all over the place here. I did not write any F or G, right? And the rest of this is just garbage, right? But it's still binary, right? Why would you want binary data? Well, let's take a look at the size here. Let me go back and, oops, not that. Let's see, Emacs, data.txt. No, I want, there we go. Instead of printing I, starting at 0 to 100, let's start it at 2.147 billion. 1, 2, 3, 1, 2, 3. Is that billion? Is that right? 1,000, million, there we go. And while it's less than that plus 100, 1, 2, 3, there we go, we'll go ahead and print it like this. GCC, run it. And let's look at the actual data now. Data.txt, there we go. So there's 2.17 billion. Well, why didn't I go higher? Because I would have gotten overflow. But there's all the numbers. 2.147 billion and change all the way up to 2.147 billion and 99. Right? Let's look at the sizes of the files now. The txt file, the plain text file, is 1,100 bytes, whereas the binary file is only 400 bytes. Why is it 400 bytes? Where's that 400 coming in? How many integers did I write? 100. How many bytes does each integer take? 4. That gives me the 400 bytes right there. Why is it so much larger when it's plain text? Why is it 1,100 bytes? Let's look at it again. Let's look at data.txt. How many bytes are on that first line? Each one of these is a regular old character, so each one takes 1 byte. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the end line character would be 11. 11 bytes per line. How many lines did I write? 100, right? 0 through 99. So how many total bytes did I write? 1,100. That's where that 1,100 comes in. So plain text, yeah, it's human readable, but it is way more inefficient, right? Not only that, but if it's plain text, if you're trying to store data for an image file or an audio file or anything like that, nobody ever needs to read that data directly. You just need to play your music, or you need to have a file viewer to show you what the picture looks like, right? There's no reason for it to be in plain text because no human would ever need to look at it and say, oh yeah, I see that, right? The one place that you do want plain text is on, again, EDI, Electronic Data Interchange. Do I have a, let me check my mail and see if I've got an example here. There might be some sensitive mail, so I'm going to bring it over here. All right, has anybody sent me an image recently? No. Okay. So let me go ahead and compose something to myself here. Here we go. I'll bring this out over here. So there I am. Let me go ahead and find an image. I don't know. Do I have any images on this computer? I don't know. Oh, here's a nice image that my son made. He was with pixel art or something like that. There we go. So it's some sort of, I think it's supposed to be a Plants vs. Zombie thing, right? So I'm going to send it to myself, right? And there it is, right? And there, I get that nice little picture there. Do you think that, how do you think that it was actually sent through email? Over here, you can actually view original. Where is it? Show original, right? There's what it looks like, right? Well, there's a bunch of metadata, and that's not actually showing me. Okay, copy to clipboard maybe, and then can we show it over here? Nope. It's not showing me the multi-part mime. Okay. Download original. Open that up. There we go. There we go. All right. All that is just text. That's a bunch of HTML embedded. There is the actual image. Right? So is that binary? In a sense, it is. But it's just a bunch of letters and letters and numbers and stuff. It's actually Base64 encoding or UU encoding. What it does is it takes all of that binary data, which is just a bunch of zeros and ones, and then assigns it to 64 unique unique letters in the ASCII text system. 26 uppercase, 26 lowercase, that gives you 52. 0 through 9 gives you 10 more, so 62. And then 2 additional ones, which I think are plus and slash. Yep, right there. Right. So 64 different actual English language characters used to encode that data. Now, on my end, on the Gmail end here, right, it's taking that Base64 encoding, decoding it, and then treating this like the PNG that it originally was. And this is because, there it is again. This is because email, very, very old technology. It was never envisioned that it would be used for a lot of binary data transfers. Not a lot of attachments back in the 70s, 80s, whenever people were using ARPANET or whatever it was. So they had to come along. Email was designed for plain text. It's really only able to handle the ASCII text system. It's not really able to handle directly a bunch of binary data. So you have a way to encode that binary data as text, and then you can send that through your email instead. And there it is in practice right there. Right? So there are lots of different ways to deal with binary. And binary is usually the go-to for a computer that, for things that humans don't need to read. Or you have other EDI exchange formats like UU encoding or Base64 encoding, or XML or JSON, and I'm not going to bother showing an example. We've got a time. XML example. All right, fine. Okay, that's really simple. Everything here's a note. It's all semantically marked up. The to, the from, the heading, the body, and then you've got closing tags like this. You'll actually be doing this tomorrow in lab. You don't have to worry about formatting XML or reading XML. You're just writing XML. And then a JSON example looks very different. It's way lighter weight. It's a key value store. So you've got the keys, which are strings, colon, and then you've got say arrays. You've got other strings. You've got numbers. Is there no number here? Okay, there's not an example of a number here. But you've got objects within objects within objects if you really want to. Just like a XML here. You have a root object, and then you've got 4 objects that belong to that object. Right? So those are data interchange formats. Again, if you ever have to actually work with binary data or data interchange formats like this, in practice, use a library. Right? Don't rewrite, reinvent the wheel and rewrite your own JSON form parser or XML parser, right? Unless it's assigned as an assignment or something like that. Right? That's basically a file IO in a nutshell. It's very, very simple. All you need to do is remember printf and use fprintf. For reading, you just remember fgetc and fgets, or fgets, depending on if you want to read character by character or line by line. Right? Any questions? No? Then when we come back on Wednesday, we'll start encapsulation.